first I like to once again thank the organizer for giving me this opportunity. The topic is very broad actually. Energy conversion, storage for flexible electronics like that. In that a small part is what I want to say, that photocatalytic materials for energy applications, that is energy production. So energy production we can able to work on it. So our research group is focused on the photocatalysis, the specialization. I can explain you in detail about it. I am sure all of you get some a good knowledge about this particular subject. And then move on for the second session in the afternoon. See, today I am going to talk on the photocatalysis for energy applications. Here, what about the interface properties like that? I will explain more detail later. First, I like to give a short introduction about our university, Yogi Vemana University. Though we call the Telugu students and the colleagues knows that Vemana is a Telugu poet and he has given excellent informations about the life and many other things as well. So the Vemana University is not a purely language university. It's a multidisciplinary university having arts and science and engineering campus we have. So the university is a rapidly growing state university in Andhra Pradesh. Here, the university has several credentials. Recently we got in the last year at the same time we got it NAC A grade. It shows the progress of the university, infrastructure facilities, competency of the faculty members and the research capabilities of the universities. And then the university having several research projects like you say that DST, MNRE, UGC funding and DBT, DST, so many fundings are there. And the university having also completed ROSA sponsored 1.0, now we are applying for the 2.0 as well. So it's a vibrant campus. So in the Andhra Pradesh state, the public universities, they rate in terms of the discipline and then response wise number one in the state. It is not ranked by the faculty members, ranked by the Andhra Pradesh State Council for Higher Education. Because in the science faculties especially, 8 out of 10 people, we are 100 plus faculty members are the regular faculties. 8 out of 10 faculty members, they worked in one of the foreign countries. They worked in a very good fellowships as well. So that is a speciality, and have a good diversity in the faculty as well, faculty's experience and then the origin as well. So by this way, the Yogi Vemana University is a unique public university. It is working very well both teaching and research in the best possible way from the state rural university like that. Next. So in our department, it's a material science and nanotechnology, the only department in the even combined state of Andhra Pradesh as well, because you can see the material science people working either in chemistry or physics or even some materials they are working for biomaterials or nanomaterials as well. So it's an exclusive department is there in our university. We are 5 faculty members are there. So everybody is working. Broadly we are covering energy, environment and healthcare. These 3 topics we are working in our university. This department is offering MSc Material Science and Nanotechnology and PhD as well. So the PhD depends on the specialization of the individual faculty members. Next slide. And we have several credentials in our department. The people has international fellowships working in USA and other countries as well. And several credentials are there in our for the department. It is listed here. And the students who completed the PhD, they are working in abroad, most of them, for international fellowships. Next. And these are some of the unique facilities available. Of course, every laboratory having a lot of facilities. So we have the gas chromatograph that I am using for hydrogen and oxygen analysis, and then ball milling for particle size reduction from micron size to the nano size. And then we have the solar simulator. So like our sunlight, we can use our solar simulator for photovoltaic hydrogen production, and solar cell application also they use it. And we have the CVD, chemical vapor deposition. We have used this facility for carbon nanotube synthesis, and particle size analyzer Once we prepare a nanomaterial or any material, we can measure the particle size, what is the range like that, and the general laboratory facilities, just a photograph for you. Next. About the departmental research profile. So our department is one of the top 1% in our university, or we can say the number one in the university in terms of research. Of course, the nanomaterials, it is playing a very important role. We can say everything around us is in materials, so that our work is very well published in leading journals in the international journals. Next. And these are some of the journals like Applied Catalysis B, which is having high impact factor, solar energy material, solar cells, chemical engineering journal, and catalysis communication, chemical communication, ACS Applied Energy Materials and Interfaces, API, ACS Nanomaterials, so many journals are there. So that shows the commitment of the, we don't say the faculty member, mainly the scholars and the collaborators as well. Next. So, and people knows Kadapa means immediately different thoughts are coming. Even my first collaborator in IAC at Hyderabad, they are afraid of coming to the Kadapa, being as a faction known place. People also proud of it for Kadapa, but not like that. It may be a part of the places, and it was old thing. It's nowadays it's a very very good ambience in Kadapa. So from that rural place also, we could able to work in collaboration with IITs. So from we are proudly say that from IITs, NITs, central institutes, the students come to work in our laboratory, research laboratory, for especially for hydrogen production experiments. And this is from IIT Mandi, Himachal Pradesh. From there they come here and worked at, and we publish in Journal of Materials Chemistry, Royal Society of Chemistry publications. So this is to say that we can able to work. Now technology has come up. We can this kind of programs. It's to interact with the people. Dr. Venkata Krishnan, who is in IIT Mandi, I met him through the Dr. Satish, the next speaker. He only introduced him, and we have interacted in another conference, and we started collaboration. Two of the research scholars, they came from IIT Mandi, northeast to Kadapa. It is a contrast in the weather. That is a cool place. Here is a very hot place, Kadapa. So, but they come to the suitable in the month of January, so that is better. And did a collaborative work. This is to say that we can able to do the collaboration, not necessarily with our laboratory. You can find a collaborator here or some other place also. You can do the good research work for the research scholars as well as faculty members telling. And the other boy, you can see, is a research scholar. He is now in South Korea in working as a brain pool fellow. So that is an international fellowship. In that, from India, 2 people are selected 2 years back. He is one among them. So one from the, I think, IIT Roorkee. The other one is he. So only 2 people got selected. He is the one, and he was only from the very rural background. First graduate from family, probably from the village as well. So everything he came up from the government scholarship only, but he is a very highly dedicated person, sincere and knowledgeable. But he has a little bit difficult in English communication only. But because of communication, his commitment, he could get excellent publications, and then he joined for that fellowship. So he got it 50 lakhs per annum in that fellowship. So we can say that packages were mostly in terms of IT fields, but he can get it in through the research as well. So putting commitment and regular work, it can give the very good output. So it is not the matter. So if I there in the IITs, then only I can succeed. Not necessary. If I are in the central institutes or in a leading institute, then only I can do it. Not at all necessary. If really committed and having good connection and really aligning ourselves towards that, we can able to do it. That everybody can understand. Next slide. And we have a collaboration with the various institutes, though we are in a small place. So having the good contacts. So I also met Dr. Satish in Japan only. Though he is just adjacent campus. I did a PhD in Anna University, Chennai. He was in IIT Madras, but we never met. But in Japan, I met him by introducing by other friends. So that contacts gave us, we completed a research projects with the excellent publications as well with the collaborative project. So I could say that I could stand in front of you for at least two I have to thank. One is my collaborator and the second one is my research scholars. So the research team, they did very good work. Next. So these are some scholars working in different institutions. Next. And then this is a small research laboratory for our research work. We have a faculty, individual faculty is having a research lab, or two people has given a research laboratory like that. I have one research lab, partly for instrumentation right hand side, left hand side for material synthesis facilities. So the facility is also shared for other colleagues in the department. Okay, next. And this facilities, everything, it is established by using the collaborative project only. I must thank these two people, Dr. M. Subramaniam and Dr. Durga Kumar from IIC Hyderabad, and I also should thank Dr. Satish. This is second project collaborator. So that Subramaniam sir and Durga Kumar madam, they encouraged me to go for a MNRE project. At that time, when I went for the presentation, they said, Yogi Vemana University, please check it whether it is blacklisted or not. At the time of project presentation, because IICT they are know very well, very old institute. They literally, he said, from BHU, I was a little bit about to cry. Why he says blacklisted or not about the university like that, whether a university is existing or not like that. So then it has given me a lot of energy and commitment. I should prove my university, not me, prove my university name like that. So we worked, fortunately we got a very good results, and we went for the first year with the publication from Chemical Communication, RSC journal. That is not easy to publish. At least in IIT or Central Institute standard only they will publish, not from the rural, just newborn universities like that. So we could able to work and we got it appreciation, and he could stand, Professor Upadhyay, at the time of presentation, first year progress report. So he approved your medal, and I'm sorry, I take back the word about your university like that, he said. I didn't talk about anything, only the work speak. So the thing is, really commitment, everybody is having commitment, I didn't deny about it. Everybody is having commitment. We get several distractions as well, discouragement by somebody else. Being a new university, I had less distraction and more focus towards our research work, and we could able to get it. I must be thankful to these people for successful completion of the two research project. The first time they ever gave it to the university. Always they gave it to the IITs and CSR Institute, not even Central University did not get it, Ministry of New and Renewable Energy. First time we got it for the university. Right, thank you. And our research group, we have published several materials in different journals. So just a few I showed here, just to make sure that we have developed more than 25 efficient materials in the last 13 years in the Yogi Vemana University. And these materials showed a very excellent activity. We also failed. Always we are talking about positive. Did you ever fail or having any pitfalls? Yes, we do. We had a lot of several time failures continuously. Once failure results comes continuously, that a month or next month also failure results only it will come. Once we get a positive result, we get the good energy level and we will get a good results. So we get both good results and also what we expected also we missed it. But the best one I am showing here. So we got a good results for hydrogen production and published in many journals. Fortunately, the first patent from our universities, from our laboratory only, for US patent and Indian patent we have for this particular work. Next. So our research group alone published in these journals, and some of the credentials already they introduced. Next. So these scholars from our research group, they graduated, all are working in South Korea in different institutes. So we know that many people are working in South Korea or other countries. Their fellowship also it varies. They are working with a prestigious fellowship, and also they kept in a very good place in their research group as well. Next. These are the scholars currently working in our research group. Next. So now going to the topic. What I explained to you so far, we had a journey, last 13 years journey in Yogi Vemana University, and I like to express that I like to thank my university for giving an opportunity, being a new university, And also, actually, I was born and brought up in Tamil Nadu, of course, a nativity from Kadapa district. But they give me the good encouragement to do the research work, the scholars and the faculty members. So by this way, we can able to work with very good results. And it is not just about, we are not expecting anything global ranking like that from my lab. So only we have to do the best research. That's it, committed, and it should be reproducible like that. By that we got it. So I think this can give some seed to some of you, the scholars, and you can work very well. Many times when we see that, sir, I work very well, I am ready to work, but other person is not cooperating, and there may be instrument down. If there is instrument down, through these places like that, you can have the contact with the people. You can find a new place where you can send it for characterization. You can go for some collaborative publication, taking their inputs as well. Need not to worry about the TM is not working, SEM is not working, or other facilities not working like that. Okay. So I like to say that so today morning lecture is a two-part is there. So first part is about the hydrogen production through photocatalysis. Second part about the thinking about scientific writing. I will give 5 minutes after this lecture, 5 minutes break, about a question answer session plus break like that. Then we can start the second part. Because if I continuously explain you about the my scientific achievement, what we have done, experimental details, it may be boring, I know, because I sat like you in the other part of the seat. After half an hour or 45 minutes, we will get exhausted in the same topic. So I have planned, we have a lot of results, but only one part I will explain, and what are the mistakes or care mistake we are doing often, or what are the care is necessary for the good scientific work also. I will explain end of this talk for the maybe for the research scholars purpose. So we have done several we have done for materials efficiency like that. The main purpose is we said it for photocatalysis. Next slide. In the photocatalysis, next. The photocatalysis, this topic is highly liked by both scientists and engineers. I mean both science and engineering disciplines, because the photocatalysis is a interdisciplinary topic. First of all, it is easy to understand. Not too many mechanisms are not involved, and need a simple facility is sufficient. Like sunlight we have, okay, and we need some of the other facilities. Sunlight we have, we need a catalyst which is a cheaper material, we can able to use it, or efficient material we can able to use it, and we can test it with some basic facility. If you prepare a photocatalyst, and it can be tested for degradation of dyes, and you can check it using just a spectrophotometer. Once you ensure that this material is good, then you can go for characterization and further activities like that. So first I like to say what is here if you talk about science, in the science also, you know, physics, chemistry, it is a partly physics, partly chemistry is there. And then when you're coming for the application, engineering is coming up. So in catalysis is a physical chemistry part. So that is a chemical substance which increase the rate of the reaction without consuming itself. It's a simple term, we can say that. So a lecturer or a teacher as a catalyst, for example, this is a lecture hall, a teacher is entering into that, and many students are sitting here. What he do, he come and teach, and then he will go away. Like that, a catalyst, and that is he teach and enlighten the student, giving the knowledge. So, but the teacher may stay in most of the classes, the students may stay in the same classes, teacher go out, and the next teacher will come. Like that, the catalyst is a chemical substance which increase the rate of the reaction. Because normally when you mix the two chemical, some of the chemical it will react, like acid and base, it will react quickly, give the product. But some of the chemical when you mix, it won't react. Even at a little bit heating, it can improve. That is also, it doesn't work out. When you use a suitable material, a chemical called a catalyst, which accelerate the rate of the reaction. So normally that catalyst also, it won't work under room temperature. many times it works under when you heat this catalyst only, because that is called thermal catalysis. Normally, in want to carry out some chemical reaction, it requires a very high temperature like 400 or 500 degrees centigrade. In the presence of a catalyst, it will work much lower temperature like 100 or 150 like that. So by that way, that is called thermal catalysis like that. So to activate the catalyst, we need a heat. So by that way, we can we talk about the thermal catalyst, and it gives the catalytic reaction. So what we would talk about photocatalysis is the catalyst. We don't need heat. For photocatalyst, we don't need heat. Only light energy is enough. Okay, light energy is enough. So just you can think about everybody, whether it's a science or engineering or any subject, we know about the plant photosynthesis. So what it do? Plants, we have the chlorophyll. It produces the like a carbohydrate can generate. So the plants, it takes the water through the roots, and then carbon dioxide from the air and also from the sunlight. It undergo the splitting of the water into the H plus and oxygen, and you can see in the bottom red color we can CO2 plus H plus and electron, it can give the carbohydrate. So many photochemical reaction or biological reactions are there. Please don't worry about it. Just it is given so many reactions are taking place for the biological purpose. The underlined part is water splitting takes place and in the photosynthesis part. Splitting is very easy. You know, split means you can make it 2 or more also. Okay, so water splitting is water, what we have, 2 hydrogen and oxygen component is there, H2O. If you split it, we can get a proton and oxygen as well. So that oxygen is released by the plant, that is good for us, whereas that proton is used for carbohydrates. Similarly, we can do the artificial photosynthesis. What do you mean artificial photosynthesis? That is, the water, we can split the water similar to the natural photosynthesis. We can produce the protons, and then it can be turned into the hydrogen and the oxygen gases as well. So by this way it is good. So we have 3/4 of our earth, we have the water is there. Okay, but sea water we cannot use directly. Even for drinking purpose we need to purify. So this water, what we do, we can split it, we can get the suitable way, get the hydrogen gas. So this hydrogen gas, it can be used as an excellent fuel. Why we talk about this hydrogen gas? So prior we can talk about environmental pollution, lot of issues are there. Using petrol, diesel, coal, it is giving a lot of environmental pollution. So what we do to overcome alternative energy sources, which is a sustainable, because using a coal or a crude oil, it is not a sustainable one, right? It is not available in our region. We are getting most of them from Middle East countries. Okay, so not to sustain what we have abundant sunlight, especially Andhra Pradesh state, sunrise state, we have abundant sunlight about 10 months in a year. So we have to tap the sunlight very effectively for to solve our energy demands and reduce the environmental pollution as well. So we can able to do it using the solar energy. This photocatalysis, the catalyst activated by the light, it cannot activate with all the light. Especially it will be activated under the suitable energy level that I will explain in the next slide. So you can understand the photocatalysis is the catalytic reaction is accelerated in the presence of the light. So it can involve oxidation and reduction reaction basically. So it can be easily understood by any engineering people. You can see the publications, journal publication in this area. You can see many science people are there, many engineering laboratories are there doing, and the majority is in the worldwide. Number 1 is China, number 2 is USA, number 3 is India, working on this topic. Even a faculty member working in a college with a simple, I can say that just to spend 1.5 to 2, I cannot say 2 lakhs as a gesture, because many research facilities they need several lakhs and or crores. This having maybe maximum of 2 lakhs rupees, you can start this research work in a systematic way, understanding. You can do a good publication, and then PhD also it is possible in this particular topic. So that you can see a lot of publication in this particular area. Next. So being the MSc students also here, we have to know some basics of this particular topic before going to the advanced level. So the principle, if you understand, it will be easy to make a new material, not only new and also efficient materials we can able to do it. So the catalyst is a semiconducting material here. Okay, not necessarily all the catalysts are semiconductor, especially photocatalyst must be a semiconducting material. So you can see on the bottom, the blue color part is again VD, that is valence band, and green part is a conduction band. The distance between top of the valence band and the bottom of the conduction band called the band gap. I'm sure all of you know in the bachelor level itself. So the band gap you have, when you irradiate the light, the energy, like sunlight also, we have UV, very small part is there, visible light is there, and infrared light, etc. is there. But we need especially visible spectrum of the solar light, because it's about nearly 45% of the sunlight we have visible spectrum, and that energy if you take very effectively, we can be very successful. So this is the any photocatalytic reaction. If you see, we have the four type of reaction. One is absorption of light, that is light harvesting. Second, charge carrier generation and separation. The bottom you can see plus symbol, and the top you can see that minus symbol, that is electron in the hole. Electron vacancy is called hole. Both undergo the recombination. That is the problem. Why it is undergoing a recombination? Because it is a Coulombic force of attraction. The charge carrier undergoes the recombination and generates a lot of heat. So if it is moved to the surface very effectively, it can be involved in oxidation reduction reaction. The valence band hole involved in the oxidation reaction, whereas you can see on the top, reduction reaction takes place with the conduction band electron. So oxidation and reduction reaction, it is sometimes called as a redox reaction. It can be carried out. So if you want to carry out some oxidation reaction, mild oxidation reaction, and you can do it using valence band hole, mild reduction reaction by using conduction band electrons. Okay, but it's a non-selective. In order to be selective, we can use a more efficient material. So what is the advantage of this particular method is, we said that photocatalysis is a very simple technique, and we can able to do it with minimal facilities also, and it's a cost effective, and this technique is why it is very interesting. It is work under ambient condition, as because many material, it is not working under ambient condition, it needs a heat. Okay, this is why it plays the sunlight and works under ambient condition, and it can produce the charge carriers and works very effectively. So that is the main advantage. The byproducts also, it is a non-toxic and harmless end products are it is giving, and we can say that the reaction, if you use for the environmental applications, it can completely destroy the pollutant, not partially. Okay. So the reaction, it can be both in a gaseous phase or a solution phase also possible. So there are several advantages are there. We know that when there is some several advantage, there is a limit also. Our challenges are there. So we in cities, people are scared for water. If you see in Chennai, during summer season, they want drinking water or potable water. Of course, they have a sea. They could not, they are now started using a desalination of that sea water and also using, but it's a more expensive process. So though it is water is available, but it cannot be usable directly. So like that, here we have several benefits for this particular method. It is ambient condition working, it's more efficient, but some challenges are there. What are the challenges? Earlier the material work under UV light only. It is now a visible light active material in the sunlight, and visible light active materials, you can see it's most of them are wide band gap semiconductor, and then band edge potentials are important, and the material should be stable. These characteristics it does not having all the material. For example, I prepare a material, that material shows very good visible light absorption, but efficiency is poor. And I have another material, it shows very good efficiency, but low stability, or it is a toxic. So this kind of one or other way, okay, some material having both, now I am going for scale up, it is not scalable. So these kind of issues are there. How to overcome this? We have to prepare an innovative method to prepare a composite type of material. So to prepare this material, we need to have the first, what is the work reported so far? What is our understanding? Very important. So by that way, we could able to do it. So one of the major issue is the photo-generated charge carriers undergoes the fast recombination. That is, recombination is we can say more than 99% it is undergo recombination. Then what else you are going to do? So recombination are two types of recombination. One is a bulk recombination, that is within the particle, and surface recombination. After reaching the surface, it can undergo a recombination as well. So in order to minimize the recombination and maximize the transfer to the surface and the reaction between the reactant as well, so we have to use the innovative strategy to improve the performance. In this, the interface is the important. So the title also mentioned about the interface properties. So if you have the suitable two materials, it forms the good interface, we can overcome that charge carrier recombination and it can improve the very good efficiency. By that way, we can able to do it. So some of the challenges are, it's a very well reported in the literature. The literature, we have the research article, you have the review article. Nowadays, it's excellent review articles are coming in some of the journals. They write very clearly what are the challenges, what already attempted, what all the gaps are there. If you are able to understand, you can overcome that challenges. That's a really very good publication and experience as well. Okay. So what is the ultimate aim is, we have to prepare a highly efficient material. It should be stable and scalable material. That's a very simple targets. So in this way, many research groups are working the worldwide. We are one among them, right? So to overcome this, to improve the efficiency, there are several approaches are there. I want to say what is the approaches we have taken is the interface property to improve it. There are different heterojunctions are there. Okay, so in this heterojunction, we can use either metal, that's a Schottky junction we say, this is semiconducting material, similar one what we showed in the previous slide, and we can use either metal or we can use a semiconductor which is having both the conduction and valence band is lower than the semiconductor one. So another one, it can be having complementary conduction band at a valence band level, so it can work. So how to do it? It's not on my wish I have given this particular levels. It is experimentally it is proven that what is the conduction band level, valence band level, this is possible to analyze using X-ray. Not X-ray, that is a X-ray photoelectron spectroscopy, XPS. It's a valence band XPS. We can able to calculate the total band gap from that valence band, what it is there, and also we can calculate the conduction band as well. So by this way you can get find the suitable material. From the literature you can select the suitable material and you can do it. On the other side, the Z-scheme photocatalyst. So Z-scheme is similar to the type 2 heterojunction only, but what happens is here both generated charge carrier from higher energy level to the lower energy level, it is moving, whereas what we are doing here, we are using the very good oxidation, very good reduction potential, well separated. It is separated into the two different places so that it is working more efficiently compared to this. So Z-scheme, it's not our approach. Z-scheme is already reported in the literature. Z-scheme materials. But what we did, there are so many publications are there, then what is your novelty, what you have done, that you can ask me. We say that we understand the material surfaces and make the suitable interface forming the heterojunction. Do you understand? To form the heterojunction material, we understand the material's properties, its semiconducting properties and the surface properties, and prepare the heterojunction. It showed a very good interesting results. So our interest was, we find the gap is, we have so many materials, we have to select the suitable material and we have to make a suitable heterojunction. That one we have did it, and apply a suitable technique. When we take two material and mix it, it won't mix quickly. So what we did is, we have synthesized material 1 and then added into the during material synthesis of the material 2, so that it is having suitable interface. That also has some limitation. Then we understood that yes, we have to go for a surfactant enabled method so that we can have the better interface like that. So if you have the good interface, then you can get the better properties like that. So whenever the scholar is doing a research work, please do understand that from the literature what is achieved and what is the gap and how I am going to fill that gap. That is very important for your research work and research publications as well. And we have the semiconductor material for the water splitting application. We have the valence band and conduction band, and we say that under light irradiation the charge carrier reaches to the surface. First one is oxidation reaction to produce the protons, whereas a reduction reaction produces the hydrogen gas, and it needs various requirements are there. All these requirements we can able to do it by using this suitable band gap, band potential, and band gap and band potential is like we say like a physics part generally. Now there is no physics or chemistry or like that. Everything it is a interdisciplinary subject now. Okay, so one has to understand, one should understand the band gap, semiconducting property, and then coming to the chemistry, that is catalytic active sites. So active sites plays important role. So there should be a marriage between physics and chemistry for the surface property of the material. So the charge carrier should come to the surface. After reaching the surface, the efficiency of the reaction is proven by the catalytic active sites, that is called, we say, surface active sites. So the chemistry people, they say that I have bronze acid sites, Lewis acid sites, then they talk about the cavities and cracks and defects, different type of active sites are there. So I am not going to detail. So those active sites plays an important role. So we should prepare a material, considering that we should prepare a material with a suitable band gap, band potential, good interface, should have the good active sites, then only you can get the best activity. So that we have done this kind of, based on this we have prepared the material. We have so many semiconductor materials are available. We have some of the material suitable for splitting into the hydrogen production, some material for oxygen production, because conduction band potential and valence band potential is very important. We have selected a suitable material. Selecting a suitable material and making the suitable interface is very important. Selecting is one part, and another one is making the interface by using a suitable method is very important. Mostly the chemical method giving the better result compared to the physical methods for this. Okay. So many materials are available, as I said. We have chosen tungsten trioxide. Tungsten trioxide is less studied and more effective for the degradation of pollutant. But for hydrogen production it was less studied, but it is having several benefits for the hydrogen production. This material alone cannot give the hydrogen production. This can work for the proton generation, that is oxidation reaction. So that we have selected this material, and we combine with the suitable that is HEP. This is, we call it as OEP material. We select the suitable HEP material and get the good performance. So how to select this material? We have taken some of the criteria. Whenever we select the material, we should have the criteria. In that, first criteria is compatibility of the valence band and the conduction band potential, and then efficiency of the material. We have chosen 4 different material, like tungsten trioxide with the TaO2, tungsten trioxide with the CDS, that is cadmium sulfate, and 2 other material as well. I am not going to explain all the material. I will explain only one material for the time sake. So it is giving a very good results. So whenever selecting the material, we should have the idea about the band potential, semiconducting property, and then compatibility, and then you should have the interface property, suitable interface properties like that. So how to prepare that material, and then how to characterize, that I will show you from the later slides. So how we have carried out the photocatalytic experiment. So we carried out the photocatalytic experiment in these 6 stages. First, once we prepare the material, we checked it, we did it hydrogen production using the reactor. This is we call as a quartz reactor. So quartz and glass, it can be used, but quartz reactor, why we use it? We want to use the UV part of the sunlight as well. Sometimes when we want to use only visible light, then we use the Pyrex reactor that will facilitate about more than 400 nanometer only the light absorption will be there. So we charge our catalyst in a electrolyte solution. That is mostly either water, pure water, or water with some sacrificial agent, and then it was allowed for the dark, and then will disperse the catalyst, and then we go for the dark absorption for half an hour. Then we have to, it is sealed with the, you can see the top, we have the rubber septum. It's not an ordinary one, it's a specially made rubber septum available in Sigma Aldrich. Each septum is about 120 rupees. It can be used for 2 or 3 experiments only. Airtight rubber septum, it was degassed. After degassing and evacuation, it was purged with nitrogen, because for hydrogen production experiment, it should have the inert atmosphere. What happened? In normally, if we have in the air, we have oxygen and then nitrogen is there. So the presence of oxygen, dissolved oxygen in the water, it can facilitate hydrogen generation and undergo the recombination. Once hydrogen is generated, undergo recombination to give the water immediately. Instead, we have to do we need to separate the hydrogen effectively, so that we need to purge with the nitrogen gas. And then we analyze the generated gas using a quantitative analysis using the gas chromatograph. This is the equipment we are well standardized, and we are using this. And then activity test using either solar simulator or natural sunlight also we have did it. So this is various steps involved in photocatalytic hydrogen production here. So one of the material I like to explain is bismuth sulfide and tungsten trioxide. These type of materials, tungsten trioxide with some other composition, it may be available in the literature. This work also we have published recently. We can see that bismuth sulfide tungsten trioxide as a efficient composite material. We have hypothesized and then we did the experiment. So how we synthesized? You can get these details also from the publication. See, we did it in a 3-step process. We did a synthesis is a 3-step process. First step is a synthesis of the bismuth sulfide nanorod by using hydrothermal technique. You can see various stages were involved. And in the second row, you can see that synthesis of the tungsten trioxide is separately we synthesized tungsten trioxide as another material. So we prepared bismuth sulfide separately, we prepared tungsten trioxide separately, and then we integrate these two by using the wet impregnation method that we have showed here, third one. Okay, and here also we have added the third material is what we call is functionalized carbon nanotubes like that, because in order to further improve the efficiency to provide the catalytic active sites, we have added the carbon nanotube. So that we called as, we did it 3-step process. We say ternary nanocomposite. We can say binary or ternary. So binary means 2 material. We have the 3 material here, ternary nanocomposite. What is the mechanism involved in hydrogen production? I can show you in the later slide. So you can understand that we have prepared the material by using very simple hydrothermal technique. The autoclave, it may be costing 100 ml autoclave, stainless steel autoclave, it may cost about 20,000 rupees, the good one. Even you can get it lower cost also, but the good quality one, it's about 20,000 rupees is required for preparing the autoclave. Right. So to prepare this material, what we have used is, you need autoclave, of course you need the chemicals that you can buy easily. You need an electric oven and a stainless steel autoclave, one magnet stirrer, and a few glasswares. So that is sufficient. If you spend 70 or 80,000 including the hot air oven, which is having maximum, it can reach 200 degrees centigrade like that. So you can able to synthesize this material very effectively. So we have prepared the material, and you can see in many material publication, you will get bored also to see many such kind of figures, X-ray diffraction pattern. Once I prepare or you prepare the material, you will check first you go for any inorganic material, go for XRD. X-ray diffraction pattern. We compare with ICSD data and we confirm that whether we have got the material or not. So similarly we checked it, the pristine nano tungsten trioxide and the pristine bismuth sulfide, and then the binary composite and then ternary composite also we checked it. So this pristine material shows the planes are matching with the standard diffraction pattern, and the composite having a mixture of both, and the third one is a carbon nanotube which is having all the 3-1. So this is a very preliminary information about the material synthesized, and now to what is our interest is to suppress or minimize the charge carrier recombination. By that way it can be effectively used for the reaction. So whether my material is having improved charge carrier suppress the recombination or not, that we can check using simple first level is photoluminescence at a given wavelength, that is PL spectra we say. That from PL spectra for the pristine material you can see that is the peak of intensity is higher, and when the intensity is lower, that means the charge carrier lifetime is better and recombination lower also we say. So by that way, compared to the pristine material, the binary and the ternary material having better charge carrier lifetime compared to your pristine material. And coming to the EIS, you can say that the material similar kind of interference like the ternary material having a better charge carrier transfer to the surface compared to the pristine materials as well. So we and then we confirm the morphology of the material. You can see these we are given for easy understanding like a nanorod shape for the your bismuth sulfide, whereas for the tungsten trioxide like a sheet-like morphology, and we have the composites that you can see the mixture of nanotubes also in the last one, ternary composites. See the materials, it is carrying a individual morphology. When we mix also, sometimes it is stable, sometimes it is unstable. So here it shows the stable morphology for the prepared material. And from HR10 also we got the interesting results about this to confirm that presence from the lattice fringes, presence of the individual material, and also in the composite material also it is there, presence of both material it is there. So we can able to confirm that the prepared material with the morphology, required morphology is there, and it shows the very interesting characteristics. And presence of this also we confirmed by using the elemental mapping. This elemental mapping also gives the very good information about each color showing different materials. What we have bismuth, we have the sulfur, we have the tungsten, oxygen, carbon, everything we confirmed as we mentioned here. So we confirm the ratio also we can able to understand here in this elemental mapping. And from the valence band spectra also we can calculate the band gap or band potential of the given material. By this way you can get the very interesting informations. We have calculated here that see the band the valence band level is 0.86 for the given material, that is bismuth sulfide, and the band gap for the tungsten trioxide is a valence band for a 2.88 for tungsten trioxide. By this way we have calculated what is the conduction band and the valence band level as well. So this also giving some more details about your confirmation of having bismuth sulfide and tungsten trioxide and carbon nanotubes in terms of chemical composition only. So once we prepare the material and characterize it, and we go for the activity, and in this activity hydrogen production we used the various parameters we need to optimize. For example, I have optimized this material. In your laboratory, you prepare the similar material, and you need to optimize according to your reactor and the experimental condition as well. It won't be universal for any laboratory like that. For if you use the similar experimental conditions, same type of reactor in your laboratory, then you're supposed to get the uniform results. You can expect the reproducing the same. So with tungsten trioxide loading, and we can see that with the x-axis you can see weight percentage of tungsten trioxide loading on bismuth sulfide, rate of hydrogen production. It shows that increasing the rate of hydrogen production with tungsten trioxide loading, that is from 3 to 13% we have did it, weight percentage. At 9% shows 4.95 millimolar per hour per gram catalyst. And you can see that for the ternary catalyst how it is showing the performance, and if we compare the efficiency of the different material the pristine material is no hydrogen production, whereas bismuth sulfate shows very little hydrogen production. Binary shows very good, and ternary shows very excellent hydrogen production. And the stability, and we compare the results using sunlight, natural and artificial sunlight as well. So we have done various parameter and optimization studies in our laboratory, and it proved that optimization is necessary, and we also said that we have the compared the light different light sources giving the very interesting results as well. So from these results, what I explained here is, so we have the tungsten trioxide, this HEP, that's OEP material, that is oxygen evolution photocatalyst. HEP, this is bismuth sulfate, is hydrogen evolution photocatalyst, and we have the another one is the carbon nanotube, that is as a co-catalyst it is working. Having suitable interface, the photogenerated electron from the tungsten trioxide undergo a recombination facilitated with the bismuth sulfide valence band, whereas the conduction band electron from the bismuth sulfide involved in the hydrogen production, whereas this one involved in the proton generation. This proton is used here for hydrogen production. These 14 protons, it is involved to produce 7H2 gas, you can see. In addition to this glycerol oxidation, water oxidation also can take place to can give the similar hydrogen production. So we have explained for only one set of experiments that we have prepared the material, and as we have the strategy to prepare a more very good interface between the material, because of this we have prepared the better efficiency, the stable material, and the enhanced rate of hydrogen production, we have achieved it. Okay, so this is the one, we like this, we have similar several things. So from our research work, I like to share some of the important tips or the suggestion to the research scholar to complete the first session of my talk. So what our research scholars generally do is, they may go through the literature and collect the identify the interesting material. And in the interesting material, they may change a little bit. For example, we have reported along with this tungsten trioxide, copper tungstate we have reported. The other person, they may use either instead of copper, he may put zinc or bismuth or something else. That's not a novelty. One should understand that why I have to add this material and which property it is going to improve. If you understand in the beginning, then you can get it a very good paper. Just changing, they reported very good activity for this material. Just I want to add a metal, one more metal or a simple changes. Okay, you can get a very efficient results by changing a parameter. That's very good. But understanding why I am doing this particular change, that's very important. Why I am doing this particular change, that is very important. By that time only you can get a very good results, and then you can reach to the very good publications. And coming to the material synthesis part, what I am telling, material synthesis part, we are nowadays highly distracted with the mobile phone and many other medias as well. When a scholar is working in the lab, immediately a phone is coming, he is highly tempted to see whose message or call like that. Okay, instead better to keep a silent mode. Whenever you are working, please don't get distracted. Sometimes a candidate, it is happening in our lab also, sometimes they get very good result, they are unable to reproduce next time. You got excellent result, you reproduce it because you did not note down. Observation notebook is there, he is not writing. Okay, he is keeping everything in the brain, he is storing. It's not an evidence, that's not a research work. So one should note down very clearly in the observation notebook, and also if possible the time. And whenever using the man testing, I did man testering. What is man testering? You can keep it for 100 RPM, you can keep it for 1000 RPM, even 2000 RPM, rotation per minute also. What is the RPM? Okay, that should be mentioned very clearly. Whenever you are taking a solution or adding, yes, I mixed a solution A with B. How do you mix the solution? Whether you take and pour it directly at 5 seconds, or do we add a drop wise? Yes, a drop wise also, how many drops? Whether a big drop or a small drop. How do you know? You take the solution A in a beaker, solution B in a burette, and also make it open, keep a timer on. So I added solution B into the A under man testing of like 300 RPM, and dropping it, adding B into the A, it took, for example, 10 minutes. 10 ml of the solution adding, then one can able to reproduce. What is our intention is, nobody else in the world should reproduce our results. Okay. So nobody else, I should get it. నాకు మాత్రమే రిజల్ట్ రావాలి, ఇంక ఎవరు ట్రై చేయకూడదు, I should be good. ఇలాంటి యాటిట్యూడ్ సైంటిఫిక్ కమ్యూనిటీలో బై న్యాచురల్లీ వచ్చేస్తాయి, బై knowingly or unknowingly. But that is a highly risky for the research work, because somebody is trying, he is not at all getting, sometimes they make complaint also. Right? It is not happening mostly. If you have a rivalry research group in other country or in our own country, they say that this material not at all giving the activity like that, then it has to be answerable also. So whatever we are giving the experimental result, it should be reproducible by others. In that case, we must first level, we should write down in our observation notebook very clearly what you have done. What is there any color change? Yes, it is from colorless to the it is changing to light blue color or pale, whatever you are observing from your eye, you can write down. This everything gives a hint for that other person. You are getting light blue color, somebody is getting light green color. When he is synthesizing, something wrong is there. He might have done something wrong also. If you have done if you have given clearly the information, the person can able to do it. And other thing, in many times when you prepare the material, washing also, wash it with plenty of water. What do you mean plenty of water? Did you put 1000 gallons of water? No. You might have taken 100 ml or 200 ml. How many times also you washed it? It may look odd. Why sir is telling like this very silly things. Actually this is very serious things also in many times. When you are giving like this, that's why when you are submitting the journal, they reject it from the editors also. We have to give the experimental procedure very clearly. It should be, first attitude is very important. What I am doing the work, I should be able to give it very clearly, so that the other person should be able to carry out the experiment and then reproduce it. If somebody else is working and that shows your work is useful, otherwise you publish means nobody is reading, nobody is citing your work, it is not at all useful. Okay, so it is very important to understand whatever you are doing the work, it must be clearly understandable to others, and also they should be able to reproduce like that. So how it is possible to reproduce, you should be able to give the information like that. Whenever you are doing the drying also, it was dried in hot air oven. Okay, hot air oven, it can work at 40 degree, 50 degree, up to 200 degree also work. How you can say? And also overnight. For you it may be overnight, maybe 16 hours. For me it may be 12 hours overnight. So you should give that how many hours you have kept it, 12 hours or 18 hours, what is the temperature you have kept it. And also please try to give the plus or minus 1 or 2 degree. We know that our air oven is not so effective. You should give that error bars also. And what is the amount of catalyst in each batch material? When you are people, you will be preparing the material, either thin films or the powder material. The powder material, what is the quantity you got it in each cycle? All these are direct reference. Okay, and then when you are going for prepared material, calcination is one step, heating at a high temperature. Calcination also we said, calcine at 400 degrees centigrade for 4 hours. How do we calcine? Calcination means you use a muffle furnace, right? You will use it from the room temperature to the 400 degrees centigrade. How it will go? What is the rate of heating? Ramp we call it as. Either 1 degree or 2 degree or 5 degree. You might have used 5 degree. Somebody will use 10 degree like that if you don't give anything. Then if you use a same material, if you use it instead of 5 or 10, definitely it will change, give the different property. Why the other person says I am not getting the material? Because he is not given the correct result. Or you use 2 degree, it will give the different properties as well. So please mention what is the ramp. I used 400 degrees centigrade for 4 hours. In the ramp is 2 degrees centigrade or 2.3 degrees centigrade per minute. Please mention. And using the ceramic boat also, it is important. What is the size you are using? For example, I use the bigger size and using like 100 milligram catalyst. And you have prepared like 1 gram of catalyst using that same size. It may be not working. Right? See, for example, in the kitchen, we have the pressure cooker, right, for cooking the rice. See that pressure cooker size, it is suitable for cooking 5 tumblers of rice. But instead I use only 1 tumbler, what will happen? Will you get the rice or not? Finally it will be charred. It will in the bottom alage untundi. So instead we should understand that it is a vessel size, everything it matters. You must give the information in a simple way and understandable way. Even once I write all these things, it will be itself a big story like that it will be, and you think about it. No problem, you can give this also, take a photographs and give the schematic. You have supplementary information in the publications, or even you can give a screenshot, you can take a video how you have carried out the experiment and keep it in that also. Many journals they are available online. Okay, keep it. By that way a person will get understand and do it. The purpose of research, what you are doing today, it is lakhs and lakhs of people done for several years. Right? With that knowledge we are doing. What we do, the next generation should be able to work it. But many times, it's not only in India or either you or me, more than 90% of the people doing the science, the mindset is not the other person should do it like that. People, I have to work, I should get the publication, no one should understand like this. It's a fate. Okay? We should have the mindset. The problem is many times we don't understand what we have to do. Okay? Then how do you say that so many publications? Yes, it is good. Publications are there, but the intention is not good. Many times, very simple thing, we say that I should not throw the tissue paper in the room. Everybody knows that after using it, throw it away. Of course, we have the dustbin. This is just a care. Like that only, one should understand. If you put a fine or a punishment, then only we will be doing. Like that, one should know, at least some people have the intention, will do it. So my intention is, you should be able to explain it. Like that, once you prepare a material 6 months back and do the calculation, it won't give you the same data. Material should be stable, you expect. After a few months, it will changes its properties as well if it not properly stored. What we stored is we keep it in a vial and put it in a